Good evening, friends, and welcome lecture on analysis of Francis and Chaplin turbine. So, up till now, in two video lectures, first video lecture we have discussed about the construction details of all turbines. In previous lecture, we have discussed about the analysis of Pelton turbine in detail. Now we are going to focus on the analysis of reaction turbines, that is Francis turbine and Chaplin turbine. So first of all, we'll discuss about the reaction turbine and first reaction turbine, that is Francis turbine. So we know that Francis turbine is an reaction turbine having radial discharge at outlet. So what is inward flow radial turbine? So inward flow radial turbine means the turbine in which the water enters from outwards and leaves from inwards. So that is central. So here we are having the parts of the Francis turbine we have discussed. So this is going to be the runner of that particular turbine. Okay, and this runner is having two diameters. One is for that runner, here the vanes are attached, moving vanes are attached. So water strikes on that particular moving vanes rotates, and as they are connected to the shaft, that shaft will rotate. So runner, it is connected with the here vanes, moving vanes. So there are, when water is entering, it is entering from the periphery, and that diameter of that runner we can call it as a here external diameter, that is called as d1 in this case, and internal diameter where the water is going, which diameter is responsible to make the exit of that water, that is internal diameter, and it is called as d1. So here for the Francis turbine, here two diameters plays a very important role. One is external diameter d1 and another is what, internal diameter d2. So therefore, the tangential velocity depends on the diameter of the runner. Therefore, the tangential velocity is not uniform as the case of the Pelton turbine and as the case of the Chaplin turbine. So in this Francis turbine, the tangential velocity at inlet is different and tangential velocity at outlet is different. That we have to remember. That is, velocity of the wheel u is equal to, here u is not equal to u1. Here it is wrong. So it is what, velocity at inlet is u1 and is equal to pi d1n divided by 60, and velocity at outlet, it is equal to pi d2n divided by 60. Okay, as the diameter, external diameter is more than the here internal diameter d2, therefore as d1 is greater than d2, the characteristics of here inward flow radial turbine is that as d1 is equal, d1 is greater than d2, therefore u1 is also greater than u2. So this is going to be our sectional view. I told, so this is going to be moving vanes are there, they are connected to the runner, and guide vanes are there, they are used to make the proper guidance. So for the analysis of Francis any turbine, we should know the velocity triangle of that turbine. So this is a vane. Okay, here we can call it as a vane. This moving vane is there, it is attached to that particular runner, it is rotating. So I told you that discharge is radial for our Francis turbine, the discharge is radial at outlet. This means that here radial means here v2 is equal to vf2, it is beta angle is there, it is become 90 degree, and therefore what, vw2 is equal to 0. So here in this case of that particular inlet velocity, general velocity triangle if you draw, then here at outlet what will be situation is there, that vw2 is equal to 0, therefore v2 will directly become vf2, and that angle beta is there, in this case it is become 90 degree. Okay, then in this case u1 is different, u1 is definitely less than u2. Okay, therefore here it is going to be there, that okay. So now here at inlet, this is the inlet velocity triangle, so it is the inlet velocity triangle. So here v1 is equal to, v1 is the component here, v1 is having the velocity of that jet coming from that particular nozzle, that component is v1, it is absolute velocity component. It is having two components, one is horizontal component is vw1, and here vw1, and another one is there, that here it is going to be vf1 is there. So VF1 is the vertical component and VW1 is the horizontal component of U1. And whatever the V1 is makes an angle with that particular horizontal component U1. So U1 means what? The blade is moving at inlet. Blade is moving with some velocity as D1 is different. Here U1 is also going to be different. So whatever the if U1 makes an angle with tangential component U, it is called as alpha. That is blade angle at inlet. This is called as VR1. So there is a relative difference. Now V1's two components we know, VF1 vertical and VW1 horizontal. Then U1 is going to be tangential velocity of vane at inlet, and the relative difference between V1 and U1 is nothing but VR1. And whatever the VR1 makes an angle with tangential component, that is called as theta, and it is called as vane angle at inlet. And now at outlet I told that the discharge is radial, means what? VW2 is equal to 0, therefore VF2 is equal to V2, and therefore VW as whole component will be represented by U2, beta angle will be 90, and this will be VR2. And whatever the VR2 makes an angle with tangential at outlet triangle, it is called as vane angle at outlet. So this velocity triangle we have to always remember, we have to make practice of drawing this particular velocity component. Now design, when we do the design of that particular Francis turbine, here U1 is equal to pi d1n. So here it is there, velocity of wheel, it is a different one. So sorry, so read as third component, velocity of wheel U1 is equal to pi d1n divided by 60, and U2 is equal to pi d2n divided by 60. So you don't consider U is equal to U1. So this is case for Pelton turbine and Chaplin turbine. So I am sorry for here. Then work done can be calculated by the formula, that is rho a v1, as u1 is different and u2 is also different. Therefore we cannot take this common. In another diagrams, another turbines we have taken this common, but here it is rho a v1 into vw1 u1 plus vw2 u2. Okay, so if this beta angle is there, that minus sign is there. When that beta angle will become acute, then that minus sign is there. But here for the turbine, that angle is plus. So rho a v1. So a v1 is represent the area into velocity, represent discharge. Therefore, this formula can be simplified as rho q into vw1 u1 plus minus vw2 u2. Okay, so this is going to be work done per second or power generated by the turbine. Then discharge is what? As the discharge is flowing along that particular periphery, therefore this is called area we have to take as a peripheral area. Therefore discharge is nothing but what? Pi d1 b1 into vf1, because I know every time I told you that vf1 and vf2 are the component of flow responsible for flow component responsible for the discharge. So pi d1 b1 is the area into vf1, that is nothing but discharge. So pi d1 b1 into vf1, where vf is also equal to discharge is always same at inlet as well as outlet, therefore is equal to pi d2 b2 into vf2, and vf1 and vf2 are the flow component at inlet and outlet respectively. So this is a we can call it as a breadth ratio is there, we can call it as a ratio of here width to breadth, width to diameter ratio or breadth to diameter ratio b1 divided by d1, and the value varies from 0.1 to 0.40. So then flow ratio is given by, that is flow ratio is given by CV, we can call it as a flow ratio vf1 divided by square root of 2gh. Okay, or we can call it as vf1 is equal to cv into root 2gh, and that is cv is called as here flow component coefficient of velocity, and it will be having value by 0.15 to 0.30. Then speed ratio is there, phi into here is equal to u1 divided by square root of 2gh, and it varies from 0.6 to 0.9. So remember for Francis turbine, that is here vw2 is equal to 0, therefore v2 is equal to vf2, and at inlet velocity triangle is going to be same as we are drawing for general diagram. Now here we can see the one numerical on the Francis turbine. So numerical is there, here we can say this numerical. So I am going to enlarge this. Okay, the following data is given for a Francis turbine. So net head for the turbine is 60 meter, speed n is equal to 700 rpm, shaft power is equal to 294.3 kilowatt, eta overall efficiency is 84%, then eta hydraulic is equal to 93%, flow ratio is 0.20, then breadth ratio n is equal to 0.1, then breadth upon okay, then outer dimensions of the runner is equal to 2 into inner diameter of runner. Okay, then thickness of vane occupy 5% of circumferential area, of the runner. Velocity of flow is constant at inlet and outlet, and discharge is radial at outlet. So what is now given? Following data: net head H is equal to head is H equal to 60 meter. Speed N is given directly notation. Shaft power SP we can denote by 293 up to 294.3 kilowatt. Then eta overall is equal to 84%, 0.84. Then eta hydraulic 0.93. Flow ratio is there. It is going to be, we can say it as a CV is given it as a 0.20, or VF1 divided by square root of 2H is equal to 0.20. Therefore, VF1 is equal to 0.20 into root 2GH. That way, breadth ratio is there. B1 divided by D1 is equal to 0.1. Therefore, we can call B1 is equal to 0.1 into D1, or D1 is equal to here B1 divided by 0.1, that way. Then outer diameter is here D1 is there. Outer diameter is D1 is 2 into inner diameter. Therefore, 2 into D2. So external diameter is D1 always, and internal diameter is D2, because it is a inward flow radial turbine. And velocity of flow V1 is equal to VF2. So here one condition is there that for turbine for here VF1 is equal to VF2. So we have calculated VF1 is equal to the root 2GH. So 0.2 into 0.2 into here 0.2 into root 2GH, that is everything we know in 6.862 is the value of what VF1, and is also equal to VF2. And discharge is radial at outlet means VWT is equal to 0. Here it condition is given, and V2 is equal to VF2. Therefore, V2 is equal to VF2. Then here using relations now we can calculate what eta overall is equal to shaft power divided by water power, and water power is equal to rho QGH divided by 1000. So shaft power is there, it is given. Water power is equal to what? Here we can call, therefore water power is equal to 294 divided by 0.84 and is equal to 350, and this 350 is equal to rho QGH. Here we are having this particular rho QGH here into last page. So rho QGH divided by 1000 in kilowatt. Therefore 1000 into 9.81 into Q into 60 divided by 1000. So this will give the value of Q is equal to 350 sorry 0.5952 if you put all the substitution. So here it will be, sorry, so here it will be, we can say that here Q is equal to, here we can say that Q is equal to 0.5952. Then here using equation 18.20, so here Q is equal to actual area of flow. So I told you that Q is discharge is equal to periphery area. We have to consider pi D1 B1 into VF1. Discharge, this is equal to pi D1. So if you put discharge value is equal to 0.5952 is equal to 0.95 pi into pi D1 0.95 into pi d1 v1 into vf1. Therefore 0.95 is equal to into pi into d1 into 0.1 d1 into vf1, but vf1 is equal to, we can say it as a vf2, and that already calculated some. Okay, therefore it will become 0.5952 is equal to 2.048 d1 square, and therefore d1 is the runner diameter at inlet. So outer diameter is equal to external diameter 0.54, and d1 is greater, e1 is also greater here in this turbine, and then b1 upon d1 is equal to 0.1. Therefore here b1 is also equal to 54 mm. So b1 is equal to 54 mm, d1 is equal to 0.54 meter. Okay, means 5.4, here we can say it as 554 centimeter, or here we can 554 centimeter, and here it will be 5.4 centimeter. Then tangential velocity u1 is equal to, we know, pi d1 n divided by 60. Therefore it will be 19.79. Then hydraulic efficiency of the Francis turbine is given by equation VW1 u1 divided by GH. GH head is there. Therefore here it is going to be pi VW1 u1 divided by GH. So eta hydraulic is given. Therefore VW1 we can calculate. So after calculation of that VW1, what they asked, now we can calculate one by one parameter. Guide blade angle alpha, that is equal to inlet velocity triangle. We have to look for that, and for that here inlet velocity triangle, we know, here we go through the diagram again. So VF1 is equal to So again here we can go for tan this alpha we determine Vf1 we are knowing, Vw we are knowing, tan alpha is equal to Vf1 divided by Vw1, and depending on that we can calculate here that angle tan theta alpha angle take Vf1 divided by Vw1 and is equal to 0.248. That way runner angle also they asked the runner angle at inlet theta we have to calculate, theta and phi inlet and outlet, theta and phi. So for that first we have to go for inlet velocity triangle. Tan theta is equal to Vf1 divided by Vw1 U1. After putting that we are getting tan theta is equal to 0.872 and this will become theta is equal to here 41 degree and 5.4 minutes. Then velocity triangle at outlet if you look for, then tan phi is equal to Vf2 divided by U2 and is equal to Vf1 divided by U2, and therefore it will become what? If you put that value, U2 will become again similarly 9.896. So I told you that U1 is always greater than here U2 in case of this particular Francis turbine. So here then afterwards tan phi we can calculate, and again trigonometry would use, and we can say that phi is equal to tan inverse of 0.6934 and is equal to 34 degree. Similarly, diameter of runner at inlet and outlet d1 is equal to 0.54, d2 is equal to 0.27 by the relation, and because double they have given width of blade at width of wheel at inlet v1 is equal to 50. Already we have calculated. So this parameter they asked us to calculate. Now we'll go see. This is a complete analysis we have taken for Francis turbine. Now we'll go for the Chaplin turbine. Again, Chaplin turbine is a reaction turbine, but here the discharge is 10 years axial. That is, discharge, the water is flowing along the axis of that particular turbine. So here is a scroll casing is there through which the water is entering, and it is entering through this particular hub is there, and for that hub or we call it as boss, and for that boss or hub the vanes are attached which are moving. So if the blades are fixed one, I told already in the previous lecture, the blades are fixed one, that turbine is called as propeller turbine, and if the blades are adjustable, then that turbine is called as what? Here Chaplin turbine. And for that hub, two diameters are important. One is internal here inner diameter of that particular hub, and outer diameter is there. This is a, I told you that this is a dB diameter of boss, and DO outer diameter of that particular runner, that is DO. So these two diameters are important, and for this also velocity triangle is similar to that particular Francis turbine. It has a idle flow turbine in there. Again, discharge is axial, so here we can say. But here in this case, what is the situation is there that U1 is equal to U2 in this here Chaplin turbine. So again, V1 is component coming from that particular nozzle. Then it is making angle alpha with the horizontal. It is called as blade angle at inlet. Then the blade will move with initial velocity U1, that is U1, and this V1 is having two components. One is VW1 horizontal, vertical is going to be VF1, and horizontal is going to be VW1. And this is going to be U1 is there. It is going to be what? Blade velocity component U1, and whatever difference is there V1 and U1 is called as VR1. So alpha is the blade angle at inlet, theta is what? Here relative component making angle with tangential direction. It is called as vane angle at inlet. And similar now as the discharge is we can call axial, then here again here also what? VW2 is equal to 0, therefore V2 is equal to VF2, and VR2 whatever angle is making with tangential, it is called as theta. So this is going to the Chaplin turbine. Now this is going to be Chaplin turbine, the draft tube is there. So here two diameters are playing a very important role here for the Chaplin turbine. Now design parameters, we can say now here it is okay. U1 is equal to U2 is equal to pi d dmn divided by 60. So pi dmn, where the dm is called as mean diameter, and it is the mean diameter of what? We can call it as a diameter of the hub, and here is the diameter of the runner. So db plus do divided by 2, or do plus db divided by 2. Work done per second. Now as here also u is equal to u1 plus u2, therefore you have taken u1 common, rho a v1 into vw1 plus vw2 and into u, because u is common. But only for Francis turbine u1 is different and u2 is different. Therefore and is equal to, as av1 is equal to q, therefore it will become rho q into vw1 plus vw2 into u. And velocity of the flow components are same in this case of the Chaplin turbine. Vf1 is equal to Vf2, and discharge, as discharge is there, it is going to be difference in between that diameter area is going to be the difference between the area of that particular hub and area of that runner, that way through that it is coming. Therefore discharge q is equal to pi by 4 into do square minus db square into vf1. So vf1, I told you that here vf1 is what? It is going to be the flow component at inlet and it is responsive for discharge. Again flow ratio is equal to vf1 upon root 2 gh. If speed ratio is there, u is equal to u1 plus u2 is equal to what? Here that here divided by root 2 gh is equal to speed ratio and it divided by 5. So this is going to be design parameters. Now here principal velocity, I told you that pi d1 is equal to pi u1 is equal to u2 is equal to pi don divided by 60. Then vf1 is equal to vf2 pi by 4 into do square minus dv square. Already it is a repetition. Now we'll see the example of Chaplin turbine. So Chaplin turbine working under a head. So H head is given now. Here Chaplin turbine is working under head of what? 20 meter. So 20 meter is the head. Therefore H is equal to 20 meter. Okay. Then it develops 11772 kilowatt. So shaft power is what? 1172 kilowatt, and power the outlet diameter of the runner is, so do is given as 3 point, sorry, do is given as 3.1 for 3.5. Then they were given the diameter of hub is 1.15, it is db. Okay. Then the guide blade angle at the entrance extreme edge of the is guide blade angle means what? Alpha is given as what? 35 degree. And then hydraulic efficiency is going to be given as here hydraulic efficiency is given as 0.88 per 88%, 0.88, and overall efficiency is 0.84. And what they asked is that the hydraulic efficiency of the turbine is given. Runner, if the velocity of whirl is 0 at outlet, means it is a radial discharge at outlet there, or axial discharge at outlet, vwd is equal to 0. Runner vane angles at inlet and outlet, runner vane angle means at inlet, so theta, and they asked phi to calculate, and then afterwards speed of the turbine. Now here we know that the Q we have to determine here first discharge, how much discharge it is flowing. So water power is equal to rho QGA divided by 1000. So and overall efficiency is equal to shaft power divided by here shaft power divided by water power, and therefore it is given, and water power is equal to rho QGH. Therefore if you put in this case eta overall is equal to 0.84 into shaft power already given. So the water power is rho QGH divided by 1000. So from this calculation, what we can get the Q, if you put substitute the all values, and the Q is unknown only, and in this equation Q is equal to coming as here 71.428 meter cube per second, so SI unit. Then by this using equation we want to calculate what? VF1, because trigonometry to calculate this theta and phi, we know the trigonometry, and for that VF1 is required. Therefore Q is equal to, that way we have to go for that what is required to calculate for that particular theta angle. So here if you go for this particular slide, then to calculate this particular theta, we can call tan theta is equal to what? Vf1 divided by Vw1 minus u1. So u1 we can calculate, okay, pi don. Then afterwards what? Vw1 we can also calculate. So depending on this all parameters required for the turbine, so for the inlet of the triangle, that we have to unknown that we can calculate, those parameters we can have to calculate. So here Vf1 is required. Therefore as discharge is equal to pi by 4 into do square minus db square into Vf1. Do we know, db we know, now q we are knowing. Therefore we can got the Vf1 is equal to 9.9 meter per second. Then we have to use the trigonometer relation from inlet. Already I have shown this triangle. Tan alpha is equal to Vf1 divided by Vw1, and therefore Vw1 is equal to, we can call it as a Vw1 we have to calculate. Now Vw1 is equal to Q we have calculated here. Therefore Vf1 is equal to 71.448. So Q is knowing now. So Q is equal to pi by 4 ds. So therefore Vf1 so is equal to 7.241. Q is equal to, therefore Vf1 we got is a 9.999 meter per second. Then from inlet triangle, tan alpha is equal to Vf1 divided by Vw1. Therefore Vw1 is equal to Vf1 divided by tan alpha, and is coming as what? 14 meter per second. Then here we got 14.14 meter per second. Then afterwards, here we have to calculate what hydraulic efficiency is given by VW1 E1 divided by GH. So hydraulic efficiency we know, VW1 already we have calculated, U1 we have to calculate 9.81, in that G we know 20, head is knowing. So U1 is equal to 12.21 meter per second. So U1 we got, then VW1. Now we have to calculate runner vane angle, that is theta, and is equal to, again trigonometric relation I told you that VF tan theta is equal to VF1 divided by VW1 minus VU1, and is equal to 9.9 divided by 14.14 minus 12.21, and is equal to 5.13. And therefore theta is equal to, here it is coming as, therefore theta is equal to tan inverse, and it is equal to 78.58 degrees. Then for Chaplin turbine, already told that U1 is equal to U2 is equal to, so we have to calculate that particular vane angle at outlet phi, we should know the parameters of outlet velocity triangle, that is VF2 and U2. So U1 is equal to U2 in this case, and VF1 is equal to VF2. Therefore tan phi is also equal to what, VF2 divided by U2, but VF2 is equal to 9, VF1 9.91, and then and U2 is equal to, we can say it as a U1, and is equal to 12.21. So is equal to 0.811 meter, 811, and phi is equal to tan inverse of 0.811, and is equal to 39.035, and is in conversion in degree and minutes, 39 degree and 2 minutes. And speed of the turbine is given by formula pi DON divided by 60, and DO is equal to knowing that parameter. So U1 is equal to U2, so pi into 3.5 into n divided by 60, and therefore n is coming as what, 60 into 12.21 divided by pi into 3.1, it is coming as 0.80. Here it is coming as 60.63 rpm. So this way we have, whatever they have asked, speed, all parameters we have calculated. So here so this is the performance we have discussed about analysis performance of Chaplin turbine. So such kind of numericals they are going to ask on this particular turbines. So for that, I am telling you that whatever the formulas are there, you have to write on one page, and we have to draw the velocity triangle rightly for each turbine. Then relation also we have to remember for each turbine, and then afterwards calculation is very easy if you know the velocity triangle and design formula of each and every turbine. So I will give you best of luck to solve the more numericals from the assignment booklet. If you are having any doubt, query, and directly ask me telephonically or WhatsApp group. Thank you very much.